All right, today we're going to continue with influence lines and actually start applying them. All right, so now you've seen how to construct an influence line, and we always construct an influence line using a unit point load that is marched along the length of the beam. Identifying the key placements for that load will help, right? Because once you know what those points are going to be, you can just construct the influence line by connecting those points with straight line segments. So what's coming up, right? Next week, we'll get into the Mueller-Breslau principle, which is another method of constructing influence lines. It's a little bit easier, less tedious, less time-consuming. It's a lot faster, actually. But we have to know the basics first. So if you've been following along in the textbook with the assigned readings, then you have read at least through section 6 of chapter 16. We're going to skip section 7 for the moment because section 7 is the Mueller-Breslau principle, right? That one's long, maybe the longest one in the chapter, actually. These first 6 sections are really short. I was just taking a look at them, and I mean, you go through sections 1 through 6 in 4 pages, right? All right, maybe 5 pages. So really short. Actually, the first 5 sections are all in the first 3 pages, and then section 6 starts on page 4. And then it's got an example in it, which is why it's a little bit longer. So worth reading, again, going through the basics, understanding this method. And then for today's topic, application of influence lines, that's going to be covered in sections 8 through 10 of the textbook. So Section 8 will focus on using influence lines for concentrated loads, all right? And section 9 will demonstrate the application of influence lines with distributed loads, okay? We'll talk about both of those in this lecture today as well. And then section 10 is about how to find the maximum loading effects using influence lines. And that's really the main point of developing influence lines, is to use them to be able to quickly identify what is the maximum what is the placement of loading that will generate the maximum effect for a given response, right? Because knowing what the maximum possible response is important for design. That's what we want to design our structure for, right? And we've already talked about how to figure that out in the context of load combinations, right? When you have different types of loads. And we also looked at, remember when we did the load placement, or you're working through that right now in homework 8, right? So considering different placements of live loads, snow loads, things like that, and comparing the moment and shear envelopes to determine what is the maximum response at any point along the length of the beam. So using influence lines, it's similar, except we're focusing on one specific response with the influence line, and then we can quickly identify what is the maximum possible value for that response based on all the possible locations of where the loads can be applied, right? So you can identify the worst case scenario for live load placement. And so that's going to be the focus of section 10 in chapter 16. And then these 2 sections in chapter 2 are also pretty short. So we're just going back to chapter 2 because that's where, or actually we skipped most of chapter 2, right? Because that was the structural loads chapter, and that's mainly based on ASCE 722. But the sections 17 and 18 are actually based on AASHTO, not ASCE 7, because it's focused on highway bridge loads and railway bridge loads. So that's relevant to influence lines and moving loads and what we're doing now. All right, so that's why that's included in the assigned reading. And those sections are also pretty short. Section 17 is a little more than a page, but most of that is a figure. And section 18 is just a page, and most of that is also a figure. So check those out as well. And I'll point out, I do have a few pages in my notes. They're not included in your notes, but a few pages that are similar to what you'll see in the textbook. All right, so before we get started on all that, do you have any questions for me with homework 8? Okay. Any questions on influence lines so far? Construction? Okay, good deal. I expect to return your exams in class on Monday. There should be time in class to do that, so we'll just take care of that in class on Monday. All right. So, as I mentioned earlier, once you have constructed an influence line, and I am going to emphasize this again, all right, influence lines are always constructed using a unit point load. Once you have that influence line, you can then apply it to any given set of loads, any combination of loads, any distribution of loads. The only criteria is that they should be vertical loads. All right, so first we'll demonstrate with concentrated loads. All right, we're going to use this simply supported beam. And we already have the influence line for the specific response of moment at C, right? So with a simply supported beam, by now you should intuitively understand that the center of the beam, right, if you have a uniform load on it, the center of the beam is where the maximum moment will occur, right? And what's the value of that maximum moment for a uniform load?
WL squared over 8.
Yes, exactly. WL squared over 8. And so it's no surprise then that our influence line shows a maximum value when the unit load is at the center, right? So this moment influence line, by the way, right, would have been constructed by determining 3 key locations or three key placements of the unit load, the 2 ends and then the location of the response, right? So since the 2 ends are a support, really all you would have needed to do is calculate the value of the moment due to a point load at C to get this point and then connect those points with straight line segments. Then you can just use geometry to determine the intermediate values, right? So the loading that we're going to consider for this bridge girder, which is 80 feet long, is a semi-truck that's traveling across the bridge left to right. So the loading associated with that truck is shown here based on the position of the wheel axles. And we're going to plot the moment at the center span for the truck load in 20-foot intervals. So this is meaning as the truck moves in 20 feet intervals along the length of the beam, how does the moment at the center point, the moment at C, change? And then we'll use that information to identify the maximum moment at the center span. So on the next page, I have a little table set up and some diagrams that we'll use to note the placement of the point loads as they move. So the very first, right, point where the truck will actually be on the bridge is going to be, right, the unit load, the front axle of 10 kips on the very end of the bridge at A. But that isn't going to generate any moment at the center of the bridge, right, because it's just directly over the support. So we have to wait until that bridge is off the support at A. So the next 20-foot interval would place that front axle at B. So we have the 10 kip load here, right? And we'll place the 30 kip load 20 feet behind it at A. So This corresponds to x equals 20, where x represents that position of the front axle. And so our moment at C, we calculate it by simply taking the value of the point load and multiplying it by the value of the influence line at the same location where that point load is placed, right? So we have 10 kips located at B times 10 kip feet per kip at B. So that's 10 kips times 10 kip feet per kip plus, all right, technically we got the 30 kip load times the value of the influence line at A, which is 0. All right, so that gives us a value of 100 kip feet. The next placement of the truck would put the front axle at C. So you'd have the 10 kip force here and the 30 kip force here. The back wheels are 40 feet behind the 30 kip load. So they're still not even on the beam yet. So at x equals 40, we have 10. I'm going to drop the units at this point to save space. So we have the 10 kip force. And then the value of the influence line at that location is 20. So 10 times 20 plus 30, which is at B now. So that's a value of 10 from the influence line. And that gives us 500. The next placement would have our 10 kip force at D, 30 kip force at C, and now the 40 kip force is finally on the beam, but it's not contributing to the moment at C yet. So we have 10 times the value of the influence line at D, which is 10, plus 30 times 20, and that is 700 kip feet. Next 20-foot interval, we have 10 kip, the front axle at E, the 30 kip load at D, and then the 40 kip load at B. So we have 10 times 0 plus 30 times 10 plus 40 times 10. And that is also 700. So now the front axle being at 100 feet, that's off the bridge. The bridge is only 80 feet long, but the rest of the truck is still on the bridge. So we have the 30 kip force at E, and the 40 kip force is now at C. So that gives us 30 times 0 plus 40 times 20, which is 800. So far, that's the maximum. And actually, we can tell, right, that that's going to remain the maximum because the next placement will put the 40 kip load at D. And so that would just be 40 times 10, which is 400. And then the final position places the 40 kip load at the support of E, so that's just going to be 40 times 0. So I'm going to go through here, and the values that are in the parentheses, the way I wrote this, those values are all just from the influence line, right? So just for record keeping, it might be useful to make a note of that. So in general, right, the total response is just the summation of any point load that you have times the influence line of the response at the respective location for each point load, right? And then if we plot those values, the moment of C values that we obtained in this table, against the position of that front axle, it would look something like this, right? Where 800 is certainly the maximum value. And the reason I connected these points with straight line segment or with dashed lines instead of straight solid lines is because it's not necessarily going to be a perfect straight line between these 2 points, right? There could be a point that we didn't calculate that's going to break that slope up one way or another. So that's why I drew it that way. Any questions on that? Okay. Now, with moving loads like this, right? So as a truck moves across a bridge, this brings us to the next page, impact load needs to be considered, right? So the effect of, and this is a dynamic amplification factor, right, to account for the bouncing of the vehicles as they drive across the bridge, like vertical bouncing. So the impact factor is historically been defined by AASHTO as 50 divided by the length of the bridge plus 125. Or if you have multiple spans in the bridge, you can use the shortest span for a more conservative impact factor. However, it says that the impact factor doesn't have to be greater than 0.3. So that means you would increase your loads by up to 30% to account for that impact. So for that previous example, the length of our bridge was 80 feet. So the impact factor would calc out to be 0.24. That means we would multiply all of our values that we calculated in that previous table by 1.24. So the maximum moment at C accounting for impact would actually be 992 kip feet. Okay. Questions? All right. So that covers really all you need to know for concentrated loads. It's pretty straightforward. We'll get into uniform loads in a moment, but at this point I want to take a minute to show you some of the stuff that you'll see in Chapter 2, those 2 sections, 17 and 18 of Chapter 2, related to AASHTO requirements for bridge loads and railway bridge loads. So this section of AASHTO basically says what, defines the impact factor and for different limit states. And what I want to emphasize here is that you only use the impact factor with point loads. We do not apply it to uniform loads, right? Only for point loads. And here it defines the uniform load that would be used for design of a highway bridge, and also the point load configuration that would be used for design of a bridge. So they say this is design tandem, and this is also shown on the next page here, where a tandem load would consist of 25 kip wheels spaced 4 feet apart longitudinally, right? And then those would be one side of an axle, and then the axle would be shown like this, where the wheels on either side are spaced 6 feet apart in that direction. So I sketched it over here in a plan view, right, where you'd have the axles spaced 4 feet apart, and then the wheels on the axle spaced 6 feet apart. A lane load, right, defined by AASHTO would be 0.64 kips per foot. And then here it goes on to describe that impact factor, and then showing some railway loadings, right? So it's a little bit different for railways. And those 2 sections in the book will cover all of that information. So now we'll go and focus on how to tackle distributed loads, all right? And this is a little bit more involved than point loads, but it's the same idea. We're going to relate the value of our influence line, right, and use that information to calculate what the maximum response would be due to a distributed load. So we'll consider an 80-foot beam, right, simply supported 80-foot beam, so pretty much just what we have been focusing on since the beginning of this lecture and the examples. And let's see what we would do if we were considering a uniform load over just the last 30 feet of that bridge. So we have 4 kips per foot, all right, magnitude of that uniform load. And here's our influence line, right, for the moment at C. Now the values, I left them off of this diagram, but we've got the 20 kip maximum, right? This is the same influence line that we were looking at before. And then over the last 30 feet, all right, I'm going to mark where that point is on our influence line. That value is 15. Okay, so say that is 30 feet. So let's first consider just a finite length of the distributed load. All right, so we'll call that dx. And if we bring that down and relate it to our influence line, the resultant point load that acts on dx is just W times dx, right? And then this value, call that y. Y is the average value of the influence line over that finite length dx. All right, so now that we've established that, right, the contribution to the moment at C, just from the portion of the uniform load that is over this finite length dx, will be W times Y times dx, right? So this is just the resultant point load times the value of the influence line. So if we want to account for the entire span of the uniform load, we can integrate that equation, right? So we have the total moment at C due to this uniform load is going to be equal to W. We can bring that out front since W is constant, right? If you had a triangular load, you'd have W as a function of X. You would need to keep that W inside the integral, but since it's constant, and I'm not going to throw anything more complicated than that at you in this class. Just as a heads up, that's what you would do. If it's constant, you can pull it out in front of the integral. So we have the integral of y dx times w on the outside. And this integral you may recognize as simply the area under the influence line. All right, over the length or over the distance that the uniform load acts. So for this particular example then, we could calculate the moment at C. The value of the uniform load, W, is given as 4 kips per foot. And then, since that integral is just the area of the influence line, that's just a triangle, right? So for determinate structures, our influence lines will always be constructed of straight line segments, right? So that's the good news. So the area under the influence line will always be easy to calculate. Meaning, even though we set up a calculus equation, you don't actually have to do calculus. So that's going to be just 1/2 times 15 kip feet per kip times 30 feet. So that gives us 900 kip feet. So just like that, we were able to calculate the moment at C due to this uniform load without doing any statics, right? Because we had the influence line already, the statics is built into that. So that's the nice thing about influence lines, right? Once we have them. And next week, spoiler, the Mueller-Breslau principle won't use statics either. So, even though it's still founded in statics, the Mueller-Breslau principle is a nice trick to get the same value and shape for the influence line. All right, any questions? Okay. Good deal. All right, so last but not least, right, I talked about this earlier. It's important to be able to use influence lines to readily identify what would be the worst case placement of a live load, for example, for a specific response, right? And as I said, you're going through one way of figuring that out by considering different spans of placing live loads, and then developing the shear and moment diagrams and evaluating the envelopes. But with influence lines, we can do that even more quickly for a specific response, right? So it won't give us the envelope along the length of the beam, right? And so it might change, right? The maximum moment at C might be caused by a different placement of, well, for the simply supported beam, it won't matter, but if you had a beam with an overhang, right? The maximum moment at B might be caused by a different placement of live loads compared to the maximum moment at C, for example, right? So you can focus at one response at a time and rapidly get the result from influence lines. All right, so here we have a simple beam with an overhang. We're going to consider the presence of a uniform dead load, right? Remember that dead load will always be present along the entire length of the structure. The presence of a uniform live load, right, which can be broken up and moved around. And the presence of a single point load, right, which can be placed anywhere because it's a point live load. So here's the influence line for the moment at B, which is presumed to have been previously determined, and this is actually pretty consistent with one of the examples we did earlier in the week. Now this is going to be a conceptual example because we don't have values to apply, but we'll just talk through it conceptually. All right, so I've already shaded on my notes anyway the area noted A1 and the area noted A2. Here I'm just distinguishing between the total area under the influence line that is positive and the total area under the influence line that is negative. All right, So now we'll investigate two different cases, all right? One to maximize the positive moment at B and another to maximize the negative moment at B. I've already got the dead load shown distributed along the entire length of the beam because we don't have a choice in that matter. But for the live loads, right, we can place them anywhere. So if we want to maximize the positive moment at B, right, and here we have the moment at B influence line, we would just want to place that live load over all of the spans that have a positive area under the influence line. So in this case, it's just one span. All right, so that's where we would place our WL. And then where would we want to place the point live load?
B.
Exactly, right at B. How about case 2? Where should we put the uniform load?
C onward.
Yeah, from C to D, exactly. So we're just putting it over the entire negative area of the influence line. And then where would we put the point live load? Right, exactly. And then if we wanted to calculate those values, right, again, we don't have numbers, but putting it in terms of what we've identified. For the first case, the moment at B would be equal to the dead load, the distributed dead load, times both A1 and A2, all right, where A2 would be a negative value that you'd input into this calculation, plus the uniform live load times the area A1, plus the point live load times the magnitude of the influence line at B, which I've noted as YB. For case 2, we would still have WD times the net area under the influence line, plus WL times A2, plus PL times YD. All right, and here I've noted that A2 and YD are negative values. So this isn't, as you can see, this isn't very difficult. It just takes some time to get used to working with influence lines, right? Questions? Okay. So my final note here is that the influence line can be split over multiple spans. So let's see. So there was an example that I showed you, but we didn't go through. It's one of the examples that is on D2L as a practice problem for you to go through. It's for a beam with a hinge. And one of the influence lines that was determined in that example is for shear, let's see, I think I have it in my notes, so it might be good if I went back and showed you. Beam with a hinge, right, okay. So this is the beam we're talking about, right? We've got a support at A, B, and D, and then the hinge is at C. So the response that I'm focusing on in this demonstration is the shear at E, all right, this location right here. And if we skip ahead in this example, that's the last influence line that's determined in that example. All right, so here's the shear at E. You can see, right, the characteristics that we've noted before. We have a discontinuous value at the location of interest, which is E. but the slope is the same on both sides of E, right? And one other thing, by the way, that this example demonstrates is that if you have a hinge present in your beam, the slope of the influence line will always change at that location, right? Regardless of the response. That's where the beam can, or that's where the influence line can change slope, right? The other time that the influence line can change slope is when you're drawing the influence line for a moment at a specific location. And so then at that specific location, for example, here, the moment at E, we have two locations where the slope changes. One is the hinge and the other is the location of interest for moment, right? So for moment, you have at the location of interest, continuous value, discontinuous slope. For shear at the location of interest, you have discontinuous value, continuous slope. Right. All right, so that's a little background information on this influence line and where it came from. So going back to our current set, where is that? Here we go. I've duplicated that influence line here for a demonstration of placement of live loads. So the example that we just went through qualitatively is on the simple side because there are only two spans, right? So there's really only two options for placing the live load that isn't the entire span. But here we have multiple segments of the beam with positive or negative areas, right? So I'm just pointing this out to demonstrate that it is perfectly acceptable to place the live load over two different spans. So you can break it up. You don't have to keep it together. All right, so if we were to maximize the negative shear at E, we would place it on AE and on BD, but not on EB. So that would be a WL placed on AE and BD to maximize, in this case, not only would that be the correct placement to maximize the negative shear, right? And I say negative because that's where the influence line is negative. But it would also be the placement that you would want to consider for maximizing the shear at E in general, because the net area that's negative under this influence line is greater than the net positive area. All right, so if you wanted to maximize the positive shear at E, you could consider placing that live load over EB only. But depending on whether, how much magnitude you have on the live load compared to the dead load, right, which is going to be present along the length of the beam, and what the magnitudes are of these influence line values, you might not actually be able to achieve a net positive shear at E, right? Because the dead load will cause a net negative value for shear at E. And it may or may not be enough to offset by placing just on the positive area for the live load, right? Questions? All right, so I'd like to remind everyone of all the practice problems that are on D2L. Last time, with extra time in class, we looked at this beam. This time, I'd like you to think about the shear at C. Right, since we didn't do shear, take a minute and practice on this one. with the shear at C. And in order to get that, you will need one of the reaction influence lines. So start by getting either RB or RD. And again, you can talk to each other if you want, ask questions as you go through it. Yep.
So in the last lecture, when you did the example for the reaction at A, was it just a straight line because A is a fixed point? Is that why?
Yeah, so why was it a constant
Yeah.
value of 1? Yeah, because it was a cantilever beam. So since that was the only vertical reaction on the beam, it has to always take the full net vertical load that was applied, right? Yeah. Yeah, so this will be different. It'll still be all straight lines, but it's not going to be,
Not just horizontal.
it won't be horizontal. Does anyone have a reaction influence line yet? Which response? Reaction at B, all right. What does that look like?
Starts at 1.44, goes down to 1.228.
Okay, so there'll be 1 here, and you're saying it starts at what?
1.44.
1.44. This value would be 1, and off. The slope is off. It's going to be 0 at D, right? 1 here. Okay, so it's going to be something like that where it crosses at D. And you said this value is what?
-0.22.
-0.22. All right. Does anyone get something that agrees with this? Yep. All right. I see some heads nodding in agreement. All right, so with that information, has anyone been able to get the shear at C or close? You can start by plotting a few things that we know, right? We know it's going to be 0 at B and 0 at D. Now maybe get the value of the shear at C when the unit load is at A. Not yet? Okay. All right, well, I encourage you to continue working through this. Oh, we've still got a few minutes left. All right, we're not done yet. Keep working. This is good. So does anyone have a value for the reaction at B when the unit load is at C? Because we'll need that to calculate the points at C for this diagram. So I'll give you a hint. Even though you didn't need to find this value to develop the reaction at B, once you have it, since you know it's just a continuous slope from beginning to end for this line, you can use similar triangles, right? So you know this value and this distance, right? Relate that to 12 feet, so this should be 0.44. All right, so now we are out of time. So I think that should be enough to get you on the right track to get an influence line for the shear at C. So we can look at that next time if we have time, but the solutions are also on D2L for you, all right? All right, well, thank you all for your attention. Have a great weekend.